ICTS. Today we have Professor Tirthankar Roy Choudhury from the National Center for Radio Astrophysics joining us. He's a distinguished theoretical astrophysicist who specializes in the study of cosmic reionization and the 21 centimeter hydrogen signals. And he's well known for developing models for 21 centimeter signal, which is key to interpreting observations from various radio telescopes such as GMRT, LOFAR, and the upcoming Square Kilometer Array. He plays an active role in the SKA Indian efforts, and he is currently serving as the chair of the SKA India Science Subcommittee. His scholarship has earned him national recognition, including the recent Peraya Foundation Award for achievement in theoretical astrophysics. And without further ado, I would request Professor T to start his.
Thanks a lot, Prayush. Welcome, everyone. So this is going to be a series of lectures on how to use gravitational wave observations to understand large-scale structure formation in the universe. So today I will just have 3 slides and then we will move to the blackboard. So these are basically to set up the motivation for these series of lectures. So as you all know, the universe is, we always say that the universe is homogeneous and isotropic, but that is a statistical statement, and that too only at large scales. So in general, our universe shows a lot of structures, and these structures evolve with time. The earliest signs of structures in our universe, as far as observations are concerned, come from the CMB anisotropies. And this is again a very well-known picture where you see things are not really the same. So this is the CMB temperature along different directions. And some points are hotter and some points are colder. So these are the famous CMB anisotropies as observed by a series of satellites, the latest being Planck. And the level of fluctuations or inhomogeneities here are extremely small. One is talking about 1 part in 10 to the 5. So really, really tiny fluctuations. The other very popular way of studying structures in our universe is through surveys, in particular galaxy surveys. So this is again, there are several galaxy surveys. This is a picture from one of them. Each point here is a galaxy, and you see there are structures here. I mean, if I just look at the large scale nature of this field, they are not distributed randomly or uniformly. Okay? You see voids where there are less galaxies, and then you will see places where there is a concentration of galaxies. Then some of these concentrations are nicely connected by what we call filaments. So this is a very rich structure, and this is popularly known as the cosmic web because of the way it appears. And the level of fluctuations here are clearly not 1 part in 10 to the 5. They are really, really large. So what has happened is from early times, the structures have evolved and kind of reached here. So clearly the amount of structures in our universe has increased. Now, what we do with these kind of structures is to study how these fluctuations formed, why were they small earlier? Okay, they were small earlier, let's take that. But how did they grow to the way we see here? And more importantly, if we then understand the structures here, can we also understand the properties of the galaxies which we are using to trace this large-scale structure? So there are there's a lot of information in this kind of surveys. In the future, the hope is, so now we are doing it with galaxies. So we've observed some galaxies which are probably forming stars, so we see the light from there. Or it could be active galactic nucleus sitting in the galaxy and then it's very bright, so we will call them quasars. So you may do a quasar survey and so on. Okay? So currently we are doing, all these surveys are in place, and we are learning a lot about not only cosmology, the large scale, really the large scale structure of our universe, but also the properties of these tracers, these galaxies or quasars or whatever we are using to study large-scale structure. Now, this is where the gravitational wave observations may open up a new window. The hope is that at some point, I mean, assuming these gravitational wave events are happening because of stars forming within galaxies and then the merger events going off at some point. What will happen is if we observe a large number of such events, we will probably have a map like this. If not like this, maybe some poorer version of this, let us say. So using that, we will have, first of all, an independent way of studying large-scale structures. It is beyond galaxies. I mean, basically electromagnetic radiation, whatever we have been doing so far. Secondly, the hope is it may give us some guidance about what kind of galaxies or objects are hosts of these gravitational wave events. Just like we understand the properties of galaxies through these kind of studies, similarly, the hope is we will understand something about the gravitational wave events, how they happen in our universe through these observations. So this is the broad picture. However, I must also tell you that this field is yet to kind of develop. You probably, I mean, you have heard lectures on cosmography with gravitational wave events. That is something which is probably happening now. People are already measuring distances to these gravitational wave events and trying to get idea about cosmology. This is something which will happen far in the future. Why? Because as we will see in the course of the lectures, you need a lot of these objects or events to do the kind of statistics which we would like to do. So clearly that is not happening now with the current data set. Maybe with like advanced LIGO, at some point, let's say if we have thousands of events which are reasonably well localized, we may be able to detect some of the signal which we will talk about. But this is a science which is going to happen probably with the third generation, the 3G detectors. And that is where I think breakthroughs will come in this. So this is a really futuristic kind of probe of large-scale structure, but it's a very promising probe. So in the course of the lectures, I will spend most of the time in telling you the kind of techniques and tools we have to model and understand this large-scale structure of the universe. The connection to gravitational wave events will be made, but towards the later part of the course. So the main part of the course will devote in developing the basics of large-scale structures. The hope is that all of you who are interested in this kind of studies will have all the tools and techniques at your fingertips if you want to model these gravitational wave events and want to study large-scale structures in the future. Now, again, two more slides. The one quantity which we measure from these observations, both of these observations, any observations of structure formation, is something called the power spectrum. If you haven't heard about it, don't worry. I will define all these things in the set of lectures. But what this quantity is, basically it measures the amplitude of fluctuations you see in the universe. What has been plotted here is this measurement of these fluctuations across a wide variety of scales. Just remember, this is plotted against wave number k. So large scales are on this side, small scales are on that side. So the points with error bars are coming from observations, and this legend tells you what kind of observations we are talking about. This side comes from CMB observations, this part. Okay. So large scales are probed by CMB, but a lot is probed by galaxy surveys. So this is lensing. This is basically the galaxies as observed by SDSS. And there is a bit coming, the extreme smaller scales are coming from Lyman alpha forest. So in this set of lectures, I will talk about how we use galaxies to kind of compute and measure this power spectrum, and how does that tell you about both the cosmology in our universe and also the properties of those galaxies we are using. If you can just remember this shape, I mean, I won't show the slides again, but I will talk about how this shape arises. Also, as I was saying, if you measure this amplitude, you will know about galaxies. Why do I say that? So this is again a plot, but now I'm plotting it in a different way. Okay, so I'm plotting something called correlation function. Again, don't worry if you haven't heard about it, because I will define all these things and how they are related with each other, correlation function and power spectrum. But this also measures amplitude of fluctuations, again some length scale. Okay, here length scale is length scale, okay, not the inverse. For example, what has been plotted here is this correlation function for galaxies, but of different brightness. So these are very bright galaxies and these are less bright galaxies. And you see their fluctuations or their clustering are different. Okay. So this amplitude of the clustering somehow knows about whether it is coming from bright galaxies or faint galaxies. So clearly, there is that information is hidden somewhere in the measurement of this clustering. This is another plot which again plots this correlation function against length scale, but here what has been plotted is the correlation function for blue galaxies in blue and red galaxies in red. Okay, blue galaxies are galaxies which appear blue because they are forming stars. Red galaxies are kind of, we call it red and dead. I mean, they have gone through their star formation process and not really active. But you see their clustering properties are different. So clearly they are forming, I mean, they are sitting probably in different kind of places in the universe. So this is the basic idea, and it will be interesting to see, I mean, once we observe gravitational wave events, where do they fall? So that will tell us which kind of galaxies are like potential hosts of gravitational wave observations. If we are lucky, we may be able to divide or segregate gravitational wave observations based on their properties, whatever you think, and measure clustering of them. And that will tell you how different kind of gravitational wave events are happening in different galaxies and so on. But again, I must warn you that this is something which is going to happen in the future. At this moment, we should be ready with all the tools and techniques we have. And that is the main kind of aim of this course. So now I will, yeah. Yes. Not only power laws as well as amplitudes also you can see. You mean the correlation function? Good. So that will depend on the mass of the halos, and that is something I will show. Okay. So if you integrate over all halos, they will basically trace the underlying dark matter. Okay, which will be basically this. Okay. I mean, plotted in the correlation function. But we don't. I mean, we will be observing some particular set of halos. For example, what this is telling us, without going into too much details, are most likely red galaxies are sitting in preferentially high mass halos. High mass halos will have more clustering and vice versa. Okay, and that is something which comes up naturally from these observations. And I mean, yeah, this is another quantity which is bias basically, and that, as you can see, the bias, which is basically the power spectrum of that tracer divided by the dark matter power spectrum, it increases with luminosity. So brighter galaxies are probably sitting in large mass halos, which if you think is probably natural, but it's very nice to see it's coming. And now, but you can make more quantitative analysis now. You can really map the properties of the galaxies to the properties of the halos. Okay, so that is all I had for slides. So now I can switch to Blackboard, and now we will start developing the tools for structure formation studies. So maybe I can take this. And I don't need the screen, so that can. Okay. So we want to study perturbations in our universe. So large scale properties of the universe is, I mean, we know that the universe is homogeneous and isotropic, but on top of that, there are structures. So the homogeneous and isotropic part, I assume all of you know. So I won't go into any details here. Nevertheless, I will write some equations to just set the notations for the rest of the lectures. So we know that if we want to, so if we have to study this universe, and this we will call kind of background. Okay, fine. Okay, let this be there, but from now on, yeah. So this is basically the homogeneous and isotropic background. So we use the word background for the smooth universe, and on top of that, there are these perturbations. And this universe is studying using the so-called famous Friedman-Robertson-Walker matrix. So basically, we write it as some G alpha beta dx alpha dx beta. And this form will be something like, depending on what signature you use, it will look. So this is the spatial part of the matrix. This is the scale factor, which measures how the universe is expanding, and then rest of the things are probably obvious. For most of these lectures, I will ignore the curvature, but partly because from the observations we know curvature is very close to zero. We are probably living in a flat universe. But if you want to add, it is not very difficult to add in the equations. Okay. We usually normalize the scale factor such that it is unity at present epoch. So whenever I say present epoch, I will put a subscript 0 here. So T naught is today. The related quantity which is observable is the redshift. Okay, it's related to the scale factor directly like this. So this is basically our redshift. And then what do you do? Given this metric, I mean, this metric you can derive assuming the universe to be homogeneous and isotropic. Then you will put it in the Einstein's equations. So what you will say is that I will put this into G alpha beta equal to, I'm now writing all the factors as much as I can, T alpha beta. And assuming T alpha beta to be defined by some density and pressure, this will lead to the famous Friedman equation. So this will be A dot square by A square equal to 8 by G by 3 sum over all the densities you have in the universe. And there's a curvature term, which for the moment, as I said, I'm ignoring. And then there is a acceleration equation, which is minus 4 pi G. Again, sum over all the components in our universe, rho I plus 3 pi by 6 square. Rho is the density, P is the pressure. Hubble parameter is nothing but A dot by E. You can combine these two equations, or you can use the conservation equation for T alpha beta to derive a relation between rho and P. And that equation will be that each component rho I satisfies this. And this immediately tells you that rho IT will be rho I0 a to the minus 3 1 plus Wi, where Wi is defined as Pi equal to YC square. So this equation will give you how rho evolves and naturally how P evolves. And that will depend on how P and rho are related. So for most of the kind of components in our universe, we can relate the P and rho using what we call the equation of state, where Wi defines that equation of state. Now, the usual equations of state are for non-relativistic matter, this Wi is 0. This non-relativistic matter contains of both dark matter and the gas, the baryons. For radiation, this is 1/3. For cosmological constant, this is actually -1. Okay, so this is all. If we now go to the next part, we define something. We usually in cosmology, we don't like working with the rows. Let me, this is down straight away. So this will be defined as rho T by some rho critical at T. And what is rho critical? That is defined in terms of all these quantities. So you can read off what rho critical is from this equation. Given that, so this is the evolution equation for H. We know how rho evolves. Okay. So what you can do is you can write an equation which will tell you how omega evolves with time. Okay. In particular, what you for a given component, you can show that so this will go as 0. So basically, again, I'm straight away going to write the Hubble parameter. So that is given by omega matter 0, 1 plus z cube plus omega lambda plus omega radiation 0, 1 plus z to the power 4. So this is going to be a very useful equation throughout, is how the Hubble parameter evolves. So Hubble parameter, as you can see, is a combination of all the densities you have. This is basically what I will loosely call matter, but it actually basically is non-relativistic matter. This matter consists of both dark matter and baryons. This is cosmological constant that does not evolve with redshift. This is radiation, which has a power 4. Now, 1 plus z to the power, no, because it will go as 1 plus z cube. A has this minus sign. A has the minus sign, yeah. So now, again, this is something we know from observations, that omega m0 is, okay, let me just go to straight away dark matter. Omega dark matter 0 is roughly 0.26. Omega baryon in today's epoch is roughly 0.05. These are approximate numbers, but will work quite well. Omega lambda is 0.69. So these will add up to 1. That is why the curvature is 0. And omega radiation, which is not going to play an important role in these series of lectures, is of the order of 10 to the minus 4. So this is including both photons and relativistic neutrinos. The Hubble parameter, which itself has become an enigma now, but it's of the order, this is a good order to keep in mind. Okay. Although omega radiation is extremely small now, because of the way it evolves, when you go to earlier and earlier times, that means higher and higher redshifts, this starts to dominate. Okay. So as a result, our universe goes through various phases. We have this early radiation dominated phase. Then comes matter dominated phase. So this one becomes subdominant, this one takes over. And finally, we have a phase which is lambda dominated, which is relatively recent. Given these values, you can work out when this change from one domination to another domination occurred. So for example, the radiation dominated to matter domination would have happened at a value of AQ, let's put the inverse here, roughly of the order of 3,500. So the redshift will be 3,500, roughly speaking. So EQ here stands for equality. So this is a famous epoch which is known as the epoch of matter radiation equality. Okay, so this is the time when matter and radiation contributed almost equally. If you go to earlier times, it was radiation. After that, it was matter. Okay. You can have another such equality epoch where matter and cosmological constant were equal, and that you can work out from these numbers. That will be like more recent. A will be of the order of 0.75 or something like that. Okay. Just for reference, the CMB epoch is of the order of 1100. Today, of course, A is 1, so redshift is 0. If you think about when these galaxies started to form, that would be redshifts of somewhere around, I don't know, 20 to 30. We don't know yet. So this would be where we probably will start seeing structures or galaxies in our universe. Okay. So this is basically the background universe, which I wanted to summarize very quickly. Now comes the perturbations. Now what do you do? So to do the perturbations, if you want to really do it rigorously the way we do background universe, what you need to do is to go back to our metric and write it as something like average or the background part plus a perturbed part. So what is written here, what it means is that in the absence of this, we can take the universe to be homogeneous and isotropic. So G bar alpha beta is that G alpha beta I wrote earlier and that FRW metric basically. But on top of that, there are these perturbations. And then what you have to do is you have to propagate this into the Einstein's equation, which also can be written as something like this. All this factor, which I'm not writing again. So what has happened here? These are basically the components which are present in the universe. They have an average, this background value, but on top of that there are perturbations. That essentially gives rise to these metric perturbations, and that will show up in your Einstein tensor as well. So the G bar alpha beta and T bar alpha beta, if you equate these two, you will get back the conventional Friedman equations. But on top of that, you may need to solve this perturbation equation. So this will be the perturbed universe in the relativistic theory. Yeah. Yes. Okay, at the moment, I haven't even said that the perturbations are small. Okay, I've just said these are perturbations. So these are the equations which you can always write. Okay, I have I have a G alpha beta equal to T alpha beta equation. I have just subtracted out the FRW part, and whatever remains, I'm calling it perturbed. Okay, as of now, I haven't said it's small. But what you are saying is correct. These equations are extremely nonlinear. Okay, that's the next point. And it is almost impossible to solve them in their full glory in the relativistic formalism. So what we always do is to basically expand this part perturbatively. Okay. So what we will do is we'll assume these perturbations to be small and we'll write down the equations. Of course, those equations will break down the moment you cannot ignore the higher order terms. So clearly, it's not going to hold till, for example, today, where we have seen all these rich structures in the universe. So there, the conventional so-called linear perturbation theory will not work. Yeah. So that is the point. So there is a relativistic formalism which is there, and a lot of work has been done for this. But it is very difficult to do all these nonlinear galaxy like formation of these halos and galaxies and so on using the full relativistic theory. So what I will do is I will not spend much time on the relativistic part, but go to something which will be more useful, and it works very well at the scales and epochs and the kind of things we are interested in. Yeah.
Start with the Lagrangian, I'm heading with the delta G alpha, or like, is it some answers you are taking? If I start with the LM itself?
No, it's okay, probably simpler than that. Okay, so you have a full G alpha beta equal to T alpha beta equation. But you know that if the universe is homogeneous and isotropic, you know what the forms of G alpha beta and T alpha beta would be. So you say that I will subtract this part from both sides. What is remaining are the true perturbations. You will get the full G alpha beta equal to full T alpha beta equation, right? That is your full general relativity. Yes, exactly, exactly. So, but yeah.
And then I subtract the normal G alpha beta.
Exactly, exactly, exactly. So that, yeah, and that will, you will be left with the perturbed part. Yeah. And when I do the Newtonian one, you will see the same spirit will work, and that may make it clear. Yeah.
Can you give a rough idea of approximately what redshift?
Yes.
We start to see the limitation.
Yes. So it is scale dependent, firstly. Okay. So small scales tend to become nonlinear early because you have seen the power spectrum has a form. So let's talk about practicalities. For example, if I want to study CMB observations, okay, the perturbations are 1 part in 10 to the 5. It's all linear. And in fact, there you have to use relativistic perturbation theory because you're talking about perturbation in radiations. What we think for the kind of structures we are interested in, somewhere between redshifts 100 and 50 is where the kind of linear assumption breaks down. And I mean, probably in the tutorial, you will be taught how to run n-body simulations. Those are the redshifts. It could be 50, it could be 100, it will depend on the nature of the simulations and the scales you are probing, is where you will set up the initial conditions, okay? Because you know things are linear and I can solve that analytically. So that is the point I know what I'm going to start with. Yeah. So these are the typical redshifts to keep in mind. Actual value will depend on the scales you are interested in. Yeah.
Why do we take perturbations to be on a background?
Okay, because when we didn't need to, and let me answer this in a different way after we actually write down some equations. Okay, not this relativistic one, but you will see what I'm talking about. Okay, so As I said, the relativistic theory is more complicated to work with, and it may not be needed for the kind of things we are going to do. What are the kind of things we are interested in? We are first of all interested in perturbations in matter. And these are basically non-relativistic matter. Both dark matter and the gas can be easily taken to be non-relativistic. Second, we are interested in scales much, much smaller than what is known as the Hubble scale. If you think about the dimension, this defines a scale. It kind of tells you the size of the horizon of our universe. I mean, it's basically the kind of size of the universe, so to speak. So if we are interested in scales which are smaller than these and in the kind of components which are non-relativistic, it is sufficient to work with the Newtonian theory. So these two will lead to equations which will be Newtonian. Now clearly what that means is, if I, as I was saying, if you want to do CMB, you cannot do Newtonian. Why? Because there you will be studying radiation perturbations. Okay, so what you are actually looking at is the temperature of the radiation along different directions. So radiation is not non-relativistic, that won't work. If I want to study the power spectrum or the perturbation at scales comparable or larger than this, again I cannot use Newtonian perturbations. Okay. So there is a limitation, but as we will see, this works out fine for most of the things which we want to do. As is done for the background universe, we treat this matter as fluids, so they have density and pressure. So what you will write is the starting point will be the fluid equations in the Newtonian limit. So let us quickly write them down. So the fluid equations will be del rho del t plus divergence of rho times u equal to 0. So remember, rho is basically a function of position and distance. I think I will use, just for simplicity, I will use t first. And u is basically the velocity.
Hello?
Yeah.
So how do you know which species are relativistic and
Sorry?
how do you know which species are relativistic and which are not non-relativistic?
Okay, okay. Yeah, this comes from a series of arguments. Okay, so if the species is relativistic, its equation of state will be different. So it will go as 1 plus z to the 4. Now we know, I mean, so for example, gas within galaxies, we know what their temperature is, okay, how they are behaving. So that part is easy to understand, that they are non-relativistic, at least in the scales we are interested in. There could be relativistic plasma going on within the galaxies and so on, we observe them, but that is not important for cosmological studies, because for most of our case, the galaxies are kind of point particles, okay, and they are basically just tracing. The bigger question is, how do you know dark matter is non-relativistic? And that is a very deep question, and that we have learned relatively recently. And what I'm saying is maybe last 20, 30 years, because before that people did not know. And that interestingly comes from structure formation studies, okay? The shape of the power spectrum tells you that dark matter has to be so-called cold, okay? So that is why the model is CDM, okay, cold dark matter. It was not, if it was not cold, if the dark matter was relativistic, we would not see structures in the small scales, okay? The small scale power spectrum would be very different from what we see today. So there were times where people talked about hot dark matter, relativistic neutrinos being dark matter and so on. Observations ruled them out. Okay, so that's really observational thing. Of course, we haven't detected dark matter, so we don't even know what it is. But from cosmological studies, they are non-relativistic clearly today. There are some subtleties here also, but I can discuss it separately if you want. Okay. Fine. So this is the so-called continuity equation. So this tells you that this is conservation of mass. The next equation is an equation for so dot is basically for the timing del del t. U dot plus U dot will be minus gradient. So this is basically the gravitational potential. And this basically is the pressure. This equation is known as Euler equation. This is something like force balance equation. So you can see the left hand side has derivatives of velocity. So that is like the acceleration. And that acceleration is driven by the gravitational force, okay, gradient of the potential. And also you can have acceleration arising from pressure, okay, the gradient of T. This is an equation for ideal fluid, otherwise you will have to worry about viscosity and other things. Again, at the scales we are interested in, these effects are less important. And the final equation is the so-called Poisson equation. So this phi is 4 pi g. It's rho, plus it's possible that there are other components of matter in the universe, but they are not clustering. Okay. A good example of that will be, this will be 3p by c square. Good example of that will be the cosmological constant. Okay, so they will drive the potential of gravity through general relativistic effects, but they won't cluster, so they won't appear in the other. Yeah. Sorry? Yes. This is the density field of non-relativistic matter, in our case dark matter and baryons. Okay, because they are the ones which are important for structure formation. Yeah. Okay. So this is the Poisson equation. So these are our basic equations. And in principle, the idea would be to solve them. But written in this form, see, these are general equations. You can solve them under any conditions. We want to solve them in an expanding universe. Okay. So the first thing to do would be to subtract out the effect of expansion. Okay, the so-called background expansion where the perturbations were not present. So how do we do that? We do that using a series of steps. First is you make a coordinate transformation. So R is your coordinate, the usual coordinate which you're talking about. You say I will write R as A times X. So X will be my new positional coordinate. How does it help? It helps in the sense, imagine the universe was completely smooth, okay? So all the points, okay, I mean, you take any tracer, it could be a galaxy, it could be a hydrogen atom or whatever. Imagine they were all expanding with the universe. For all those tracers, X would be constant, right? Because you have to make sure that R just expands with A. So as long as universe is smooth and everything is expanding with this background expansion of the universe, you won't see any variation in X. Okay, X will just, whatever X value something had, it will just have that value throughout the evolution. So perturbations are captured very well by any changes in X. If I go and look at changes in R, I mean, just by looking at it, I may not be able to understand whether it is happening just because of the expansion or it's because of perturbation. X in that case is a very nice coordinate to work with. So again, names, these are called co-moving coordinates. These are called proper or physical coordinates. And if you are wondering why did I put subscript R in all these gradients, it's because of that, because now I will take gradients with respect to X. That is the first part. The other part is all these quantities I wrote, let us again subtract out the background part. So what you can do is, you can define new quantities. So now let me just write this thing clearly. Ex to be rho. That's the first quantity of interest, and that will be like very important throughout this lecture. This is known as density contrast. So rho is the actual density, rho bar is the average density or the background density of the universe. So rho bar does not depend on the position. Okay, it's just one number per time. And then you subtract out 1. What will happen is, if the universe is smooth, this delta will be identically 0. Okay? So that is the best part of delta. It's any non-zero delta tells you that there are perturbations or inhomogeneities, and it's a dimensionless quantity. Yeah.
So, is an upper limit on the scales at which this treatment is valid, which is less than 3/8?
Yes.
So when you're taking this average of rho, what scales are you averaging?
So yeah, this is basically average. This is like you are averaging over the whole universe, essentially. So this is this rho bar. So yeah, so that is something
Independent of the street.
exactly that is independent. So I'm just average. So yeah. So I'm averaging over the whole volume of the universe. Yes. Yeah.
The Euler equation.
Yes.
We wrote in the Eulerian description, right? Not in the Lagrangian, not in the co-moving one, to balance the force. So I am asking, when we are moving in the universe, so is the fluid equation, when we are sitting in the fluid, we choose in that direction to write the fluid?
No. So okay. Currently, we are not talking about Eulerian and Lagrangian. These are not equivalent to Eulerian and Lagrangian.
Yeah,
Just
but I'm wondering about the fluid equation.
those are Eulerian equations. Yes.
Is it correct to move to a co-moving one and then use the same equation? So that's what I.
Yes, that is what we are going to do now, right? So that is why I made the coordinate transformation.
Euler equation is the Lagrangian description. Like when you
So there is no Lagrangian. So this co-moving is not Lagrangian.
Oh, okay. It is a fixed point. Oh.
It's just another coordinate system which is defined like this. Lagrangian will be something where I basically sit on the fluid and move with it.
I'm not sitting.
No. I have just a different grid. So initially I had this grid, which was fixed, okay, and it was not evolving with time. Now I have a grid which starts with like this, and in some next time it becomes this, and in some later times it becomes this. Okay, it's still a grid. Yes.
Everything is done in the Eulerian.
As of now, yes. So now, I mean, since you asked, see, the fun now is, suppose you are in this original grid and imagine there were some particles initially here. Okay, and later, maybe in the same grid, so let me try to draw this, they moved, okay, each one moved to some other place. Now here, it will be very difficult to make out whether that was because of expansion or because of any peculiar motion. Here, what will happen is, initially maybe they were on the grid. Now if they have moved out, if they are not on these 4 points, you know something has happened, some perturbations have happened. Okay. So it's the same grid, you are still talking about grid, but it's just that the grid is expanding with the universe. So that's why it's, maybe a better name would have been co-expanding, but it's called co-moving. Okay. Till now, we haven't come to Lagrangian coordinates. Okay. Now, the way we did subtract out the average part of the density, we should do the same for the average part of the velocity. So here what is done is define something which is v, which is defined as a times dx dt. If we are talking about particles, then this is basically u dx minus a dot by a r. Again, the idea is very simple. This was the total velocity. What you have subtracted out is the Hubble expansion part. Okay, this is h times r. So whatever is left is the effect of perturbation, and this is called peculiar velocity. And the other quantities are basically part of pressure. So Ptx will be equal to the full P minus P bar. I'm not writing all the equations again in full glory. Phi will be some phi bar, oh no, this small phi will be some phi bar, phi minus phi bar. The point here is that this P bar, phi bar, rho bar, these are the ones which will satisfy the background equations, that is the Friedmann equation. Now, this I think will be a problem in one of the tutorials. What you can do is you can put all these things back, okay? There are a lot of steps involved, but otherwise it is straightforward. And now what will happen is you will end up with the equation for written in terms of these deltas and v's and these p's. And on top of that, the spatial derivatives will be with respect to x, not r. So again, I will just write the equations straight away, and hopefully you will be able to derive at some point. So this is peculiar velocity. Come here, then the equations will be delta dot plus 1 by a grad of. I mean, you can almost read them off, but you may have to just worry about these factors of 1 by a. So this is a continuity equation. You can see this rho dot is replaced by something like a delta dot. And this gradient of r is now replaced by gradient with respect to x. From now on, we will mostly work with respect to x, so I'm not putting a subscript x anymore. So gradient is gradient with respect to the co-moving coordinates. And then you have this combination of rho and densities, and v dot plus a dot by av plus 1 by a v dot. Right. And then del square phi equal to 4 by g rho bar square del. So these are the equations which tell you how the perturbations evolve. And now you see why I was insisting on writing the equations, for example, Einstein's equations, in terms of separating the background part and the part out part. Because if I just write the full equations, they will be these equations, and it's very difficult to get in. I mean, these are correct equations, but it's very difficult to get insights just looking at them. If you write in this form, now you will be actually solving for the perturbations in appropriate coordinates. Okay? So that's why you take out the things we think we know very well, okay, and go into things which we want to really solve now. Yeah. Correct. Yes. And those background equations will be equivalent to Friedmann equations. You will see. Okay. So what you can, I mean, anyway, you derive, I'm sure in the tutorial it will be derived, and if there are more questions, we can address them during the tutorials or later. Okay. Now this, I have written assuming there is just one component in the universe. Yeah. Tell me again.
This Newtonian part.
Yes. This is assumed right while writing these equations. Yes. So other way of saying is that suppose you start with the general relativistic equation, you start with T alpha beta covariant derivative beta equal to 0, then take these limits, you will end up with these equations. Okay, that's another way of looking at it. Yes, okay, because density as far as we know will never go to 0. Density is like a positive quantity. That is not true for velocity, because if I had divided by velocity, I mean, disasters can happen at places where the velocity is very small. Same with pressure. Okay, so that's why density we can do this, for the others we don't. Okay, so velocity we can go from minus 100 kilometers per second to plus 100 kilometers per second with very small values in between and so on. Yeah. Okay. Now this is like for a particular component of a fluid, but remember we have two components, right? We have dark matter and baryons. So strictly speaking, I should write two sets of equations, one for dark matter and one for baryons. So let me write that. So what I will do is I will use this to write the dark matter part. So let us call these things as dark matter. And I will just write another set of equations for it. See, there is no phi dark matter. Phi is the gravitational potential, which is contributed by both dark matter and baryons. Okay. For dark matter, there is no pressure, even at very small scales, which we are interested in. That is our understanding so far. As I said, we don't know what dark matter is, but we seem to see from observations that they are forming structures to smaller and smaller scales, though there are controversies which have appeared and gone away as to what happens in the small scales. Okay? So for all practical purposes, we can treat dark matter as what we call collisionless and ignore this pressure term for dark matter. Okay, I will write this equation later, but let me write the baryon equations. They are almost the same, but let me still write. And then phi will remain the same in both the equations. For baryons, there can be pressure. Okay. These will arise because of collisions. I mean, your standard kinetic theory of gases, P equal to NKT kind of. Okay. And this now we have to be careful because phi is a gravitational potential and that is contributed by both. So del square phi will be this one times rho bar of dm, delta of dm plus rho bar of baryon plus, into delta of baryon. This is my full Poisson equation. And this is basically the set of equations I should solve if I want to solve for both dark matter and baryons. And then there's a full coupling happening here. This Poisson equation, you can write it in a slightly different form. by, so what will happen is this will be 3h0 square by 2a times omega dark matter 0 delta dark matter omega baryons, where what you do is basically you introduce this rho critical because you have all these 4 pi g's here, and then rescale the densities with respect to that rho critical. You will end up with this omega p, and appropriate factors of 2 and then 3's will come, and you will get something here.
The omega for barrier, we put that also in 0, right? Omega, like equation of state. But here we are taking the approximation.
Yes. Yes. So what happens is it depends on the scales. So for example, so what happens is if you go back to that equation, what will essentially the two things you are going to compare is rho and p by c square. Okay, these are the two comparisons. Now for baryons, rho will be essentially the rest mass energy. P will be something like nkt. Okay. So what will happen is it will be the energy, kinetic energy of these gas particles divided by their rest mass energy. That will be the ratio. And that by definition, if it is non-relativistic, they will be small. In perturbations, what will happen is the average pressure may be 0, but there could be perturbations on top of that. And we may be interested in small perturbations, 10 to the 5 or even any order, okay? So here I cannot neglect that pressure, and that is the thing, right? When we do kinetic theory of gases, this is what we deal with, right? But for dark matter, even that pressure is probably not present because we don't see, it is really, really cold. So gases we see having temperatures of 1000, 10 to the 4 Kelvin throughout. Dark matter is probably much cooler. On top of that, they may be much heavier also. Okay. So for dark matter, even till small scales, neglecting that pressure is fine. On top of that, they may not have interactions. Okay. They have to come close. They have to have some equivalent of van der Waals force or whatever you use. Okay. Of course, we don't know, but it looks like at the scales we are interested in, they don't play any role. Yeah. Sorry, you had something else? Yeah.
Radiation of P is given by say Boltzmann type of equation.
Yes.
So for dark matter, it is observed there.
Yes. As of now, we don't have a very strong evidence for this not to be zero. Very soon, putting it for completeness, very soon you will see that even this pressure for the scales we are interested in is not going to be important, okay, towards the end of this lecture. Now, I will make the next simplification where you see this quantity. We already know that omega dark matter to omega baryon is kind of the order of 6 from the 5 to 6 from the kind of numbers we have written. Okay. And what we know and we will also show is that the delta dark matter is always greater than delta baryon. So for all practical purposes, what we can do is we can neglect this stuff. This is not a very good approximation. So if you want to do really research based studies, you should keep this. This is just of the order of a few, okay? It's not like 100 or 1000. But it will make the calculation simpler if we ignore it for the time. Okay. So firstly, you will see, they are basically following the same gravitational potential which is dominated by delta, the dark matter. So only thing which appears for baryons is the pressure. And pressure, if at all, will resist growth of perturbations. Okay, pressure is something where you try to put things like collapse things or you put your piston down. Pressure is something which constantly resists that. Okay. That is at much smaller scales. Yes. So there, I mean, even these equations, all your viscosity and various other things come into play. But with these equations, I will show that at least, I mean, qualitatively, we understand that it is pressure which basically does not allow baryons to collapse. I agree, but yeah, galactics, see, the galactic centers, it's true that the baryon fraction is larger, but that is like, it's a completely different physics which is happening. Yes. We will come to that. Yes. I mean, not, okay, we'll come to that. It's not like we are interested in measuring the density of our universe at a given point. We are interested in doing statistics, like what is the average density, what are the fluctuations in density as a function of scales, and these quantities which give rise to those observables. Okay. So yes, so they are related to the observables, but except for few like very close by universe, we really are not interested in making a density or a velocity map for cosmological studies. Yes. For the time being, yes. Yeah. So you mean phi and phi bar? Yes. Oh, here. Yeah. Yeah. So what is the question here? So what I'm saying is this term is much smaller than this. So Poisson equation, yeah. So del square phi equal to some rho. Okay. So that initially I wrote the equations only for one component. But if there are multiple components, what will happen is the gravitational potential will be determined by masses of all the particles in the universe. So what you will do is, so then this is the correct equation to write. The dark matter part and the baryon part. If there is something else contributing to it, that also you should write. Okay. Yeah. Yeah. The other thing is, sorry, I have, yeah, no, fine. This is fine. Okay. The rho rest and p rest will go in the background equation. So that has been subtracted out from this phi bar equation. So this is fine. Okay. So now what does this mean physically? So this approximation tells you that the gravity is basically determined by dark matter. So dark matter, when it moves, it really doesn't care about baryons. Okay, so dark matter, it follows its own continuity equation, its own Euler equation, and in the Euler equation there is a gravitational potential that is determined by itself. Okay, so the dark matter part, if you take these three equations, they are all with this approximation now. They are basically closed in terms of dark matter. Okay. And baryons don't appear here. So because of this approximation, we are making the assumption that dark matter just is a dominant component of the universe, so it doesn't care about where the baryons are. It just collapses under its own gravity. Baryons, on the other hand, they have their own continuity equation, their conservation. Their force equation has a phi. That phi is determined by dark matter. Okay, that phi is not determined by the baryons themselves. So dark matter will do whatever they want. Baryons, at least gravitationally, will simply follow them. Okay, because of this approximation we made, that is the physical picture which will emerge. Now these are equations which you can try to solve, and in simulation, and you will learn about simulations in the next tutorial. Some version of these equations are actually solved, not exactly this equation, and I will tell you what kind of equations are solved, maybe 2-3 lectures down the line, but this is something which one can solve in principle. If you want to still get more insights, what we can do is, for the time being, we can assume the perturbations to be small and just retain the first order terms. So that will be what we call the linear perturbation theory. So linear perturbation will give you that for dark matter, there will be this term, and then there will be a 1 by a divergence of V. Because there is a delta times V, but they are second order in perturbations. So ignore. And then there will be another which is V dm dot plus Hubble times V. The next term can be ignored. 1 by a grad phi. And Poisson equation is already linear in perturbations, so we don't have to write it again. So there is this Poisson equation here. Ph naught square by 2a. You can count the number of variables, unknown variables, and the number of equations are actually same. So this is a closed system which can be solved if the initial conditions are given. What you can do is, again, I mean, you may be doing it in the tutorial. You can manipulate this equation and, for example, write an equation for delta. So what you will do is you will take derivative of the first equation. So you will have a delta double dot. You will end up with a V dot, but V dot you can get from here. Okay. And there is a divergence. So again, divergence of V, you will put back delta dot here and so on. So you will end up with equation which looks like this. Again, remember, this is just saying that
your legs should worry
dark
you
matter
about
doesn't
potential
care about
blood
baryons. You can just solve the dark matter equations on their own. This will be the master equation for solving for
attack.
density context. Yeah. All perturbations. Okay. So delta V, if there was pressure P. Okay. So we will not have anything which is second order in any of these perturbed quantities. Yeah. All these will be ignored. Now again, before trying to solve this, let's look at this equation. So suppose I forget about the expanding universe for the time being and work in the standard like static universe. Okay, so what I can do is I can just put a equal to 1 throughout. So that will be like the universe we are like we are familiar with. Okay. So in that case, this term will go away. So what will happen is you will have a delta double dot equal to something times delta. This, and that something is positive. So what it mean is it will have exponential solutions. One will be exponentially growing, another one will be exponentially decaying. Now the exponential, if you wait long enough, the exponentially decaying term will just become subdominant, and exponentially growing term will keep on growing. Okay. So that is the thing. Even if you start with very small values of delta to begin with, they will start growing exponentially in a static universe. This is known as gravitational instability. What it essentially means is, suppose I draw rho versus some scale here, some coordinate here, and suppose you had some small fluctuations. So this you have to imagine to be small initially. Now anything which is overdense will have more mass than the surroundings, and they will start attracting mass towards them. So anything which is slightly overdense will grow more in density, and the mass will clearly come from the nearby areas which are underdense. So they will basically go down. Okay. So even if you put some small inhomogeneity in the universe, it could be as small as you want, gravity will make sure that they grow. Okay. So this is, as I said, called instability. It's a property of gravity that you make small perturbations, they grow. Yes. No, which one? Sorry. The exponential decay will be whatever, that will just go away. Yes. So I agree. So in the real universe, this is not valid, but this is exactly what happens. So this is just to give you an idea about what is gravitational instability. Yes. So the exact solution won't be valid, but the physics will still be valid. Okay. So you start with small perturbations, and put in gravity, those perturbations will keep on growing. It's much easier to show using linear theory in terms of equations, but in general, this picture is always true. Yeah.
It can be neglected even in the early universe as soon as the dark matter decouples from the
Which term?
the 2 a dot by a delta dot.
No, that it's not that obvious. I mean, so what do you mean by decouples here? So I will talk about halos. So there is no halo here. Okay, so at this moment, this is just increase in the density field. Okay.
Dark matter region becomes denser and denser. At some point,
At some point, yes.
does not it stops expanding with the expanding universe.
Yes. Yes. Yes.
In that case, also this gravitational
That is gravitational instability.
stop.
What?
When does it stop eventually?
Why doesn't it collapse to a black hole? It is random motion, non-tangential motion. So that will hold on. Just like the moon is not falling on the earth. So yeah, it's a more complicated equivalent of that. But anyway, don't worry others. I mean, we'll do this in more detail about halos and other things. I will talk about them. Okay. So this is gravitational instability. Now what happens is, I talked about exponential solutions, neglecting this term. This term acts like what you call friction or drag term. Okay, so you see it appears like a frictional term. So that is another term which because of the expansion, the things won't collapse as easily as they would have liked to otherwise. Okay, so expansion kind of tries to hold collapse. And if the expansion becomes exponential, like when it becomes lambda dominated, then collapse will become more and more difficult. Okay. So of course, the challenge in structure formation is to solve equations like this and quantitatively show that if you start from CMB, you get things which match with the universe we see around us today. Okay. Yeah.
If I like this, I just put dark energy equation also ad hocly, like rho equals to minus. Would it, there is gravitational instability still persist?
No. So we know that these kind of matter components don't cluster. Okay. So you can write down the equations, let us say linear equations, assume they'll be small, they won't grow. Okay, so that is why we don't worry about dark energy in structure formation studies, except for the expansion of the universe. They will appear here, right? A dot by A, I mean, or yeah, exactly, or a, yeah.
But dark energy should have a significant pattern. So I'm saying why we are ignoring that.
They are there. As I said, A knows about dark matter, dark energy. That A knows about dark energy. See, it was there initially. See, it was here. The full equation had dark energy. Then I subtracted out the background part, and dark energy went away. Why? Because dark energy does not cluster. It does not appear in the clustering part. If you come up with an exotic model of dark energy which clusters, then you will have this equation, and a set of equations for that component. You have to write them. Okay. So the lambda does not cluster, or this standard quintessence and things like that. So that's safe. Yeah. What happens there? Yes. 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 So do you think they cluster these K essence dark energy? But we don't see that there are signatures of clustering in the galaxies. Okay, so observationally, we know there is no obvious signature of dark energy at small scales. So yeah, so even if they are, they will be severely constrained then, because we don't see their signatures. Okay, so but as I said, if you think there is a model where you want dark energy to cluster, there's no problem with the formalism. Okay, you will just add a few more equations and you can solve them. Okay, I mean you may have to solve them in a complicated, like in a computer, in a complicated. Here, as I said, I'm assuming things to be lambda, so they don't cluster. Yeah. Okay, so now, yeah, I think we can go on for 10 more minutes, that's fine. So this equation then can be solved. So the standard way would be to write delta dm, which is a function of t and x, to be you do some separation of variables. Since there is no explicit dependence on x here, this fx will just be there throughout and it won't play any role. What will happen is we will end up with the equation which is d double dot plus 2a dot by a d dot equal to 3 by 2 h naught square, the omega value, and d by a cube. And this is a second order linear differential equation. It will have two solutions. And you can work out what those solutions would be. You can show that one solution is d proportional to h, the Hubble parameter. Unfortunately, this solution is not interesting for us because it's a decaying solution. H decreases as the universe expands. Okay. So there must be another solution. So if you know one solution, you know you can always find the other solution using some Wronskian. And the other solution, now I am making an assumption that we are living in a matter-dominated universe. So now I am ignoring dark energy even in the background part. Okay, this is only done for simplicity. In that case, the other solution is D proportional to A. So I have put lambda to be 0 here. If you don't put, you can still solve this equation. It will have two solutions. And you can see what they are. I will leave it for you to work on that. So this is the growing solution. Yeah. Which type of answers? Okay, first of all, you can always try separation of variables. But in this case, you can see there is no explicit x dependence, right? So any x dependence will just sit outside. So this equation will only allow you to solve the temporal evolution at a given point. So there is no x dependence, there is no coupling between any x to x. Okay, so this is the most general solution you will end up with. Fx is nothing but the initial configuration of the field as a function of position. And what this is telling you is that as long as linear theory is valid, all points in our universe expands the perturbations grow exactly by the same factor. And this point does not talk to the other one and so on, as long as it is linear. Okay. Yeah. No, I mean, actually you have to solve it. But I'm saying that you can, okay, I'm telling you this is a solution, you can put it back and see. Otherwise, you will have to solve. I mean, yeah. Now, so for a large part of the course, because I want to do things on Blackboard and analytically, I will assume lambda to be 0. So it's as if like I have I mean, all, whatever I'm doing is valid up to redshifts of 2 or something like that. But the general kind of formalism is fine. So you can put lambda, and you may have to find like different ways of solving these equations, but they will still be valid. Okay. So then what happens is that basically tells us that for all practical purposes, our delta dark matter will be something like what we call d plus of A times some fx, which I told you is some initial configuration of the field. D plus is normalized in such a way that d plus today is 1. There is another solution which is d minus, but that we are not bothered with because that will decay. A. For matter dominated universe, it's A. Just be careful, huh? Because when lambda becomes important, it's not A anymore. Now then various interesting things happen. Okay. If you look at this equation, del square phi is basically delta dark matter by A. So as long as things are linear and you are in a matter dominated universe, the gravitational potential does not evolve at all. Okay, it's like frozen to its initial value. What about the velocity? Velocity you can, that is the time evolution you can get from the continuity equation. You can show that the velocity will be proportional to basically A times d dot. Now this is often written as just conventionally A times d plus, which is a function of A, times HA times FA, where FA is basically d ln d plus by d ln. You do whichever you think is correct. I think continuity will be better. It's obvious, right, from the continuity? Yeah. So, yeah, you just, so this is how it is written. What you will be able to show is that for this, sorry, for this matter dominated lambda equal to 0 universe, this will be identically 1. Okay, Fa. So velocity fields will evolve as A times d plus A times h of A, where d is itself evolving as A. For other kind of lambda CDM universes, there are fitting formula which are available for F, which you can use. So one which is often used is F of Z is very close to omega m to the power something like 4 by 7 Z. There are more complex fitting formula as well. I just wanted to do one more thing, but I won't give you all the steps. You can try to do it yourself, or I think it will be done in the tutorial. This was all about dark matter. You can do the linear theory for baryons as well. Okay. So what will happen is these two equations will be same, except phi will not be now given by the baryons, but dark matter itself. So you will end up with an equation which is very similar to this, except the right hand side is now given by baryons. There is another difference. In the Euler equation, there is a pressure term which is sitting. So that term will also appear here. So let me anyway just spend a couple of minutes here. So I will go back to that part and write the final few equations, and then we will stop. So yeah, so before I do, there is one more point I should mention here. Let us look at the number of equations and the number of unknowns, okay? So I have one equation here. There are three equations here, okay? And I'm assuming that phi is already solved because it has come from the dark solution of the dark matter. So I have four equations. How many unknowns? There is one which is delta. There are three, velocity 4, but there is this pressure also. So I have 5 unknowns. So I need one more something to close this equation, and that is usually given as a relation between pressure and density. So that is the equation of state. What we will do is we will describe that equation of state in terms of the sound speed. Okay. So pressure I will replace by the CS, which is the sound speed, and I will assume that sound speed we know. Okay. So that is how you close the system. So going back then to the linear equations. You will end up with an equation which looks like this: delta B double dot plus 2A dot by A delta B dot minus CS square by A square del square delta B equal to 3 by 2 H dot square omega dm0. Now at this point, we will do something again which will be useful throughout the course. See, this equation, now, I mean, as some of you were asking this separation of variables for the dark matter case, in this equation that could be tricky because now you see there is a del square Laplacian of delta B is sitting here. Okay, so it may not like separate out neatly. So in these cases, what you do, particularly if the equations are linear, you go to the Fourier space. So what we will do, I'm writing as delta, but it holds for every parameter of interest. So I'm writing this fully because Fourier transform have different conventions for different people. So I'm going to use this. But any conclusions we draw won't depend on the convention. But whatever convention you choose, you have to just make sure you follow that throughout. This is my convention for Fourier transform pairs, okay? Now if I put this back and write in terms of the Fourier components, what will happen is these two terms will remain the same. This del square will pick up a minus k square, okay? And the right hand side will remain the same. So what I'm doing is I'm saving some time and I will just put a plus here and make it k square. Now all these delta B's and delta dot dm's have become functions of t and k, not t and x anymore. And now this equation looks like a harmonic oscillator kind of a equation, right? So you have this restoring force, and that restoring force is basically driven by the pressure term. Okay, so if you try to increase or move delta from its zero value, the pressure will try to bring it back to zero. Okay, so pressure always resists growth of perturbation. This is the driving term. So perturbations are being driven by the dark matter fluctuations. Why? Because dark matter fluctuations are driving the gravity. And this is the friction term, okay? The drag because of the expansion of the universe. And then again, you can solve. What you need is you need some idea about how CS varies. And that is again very complicated. You have to know the thermal history of the universe because you have to know how temperatures evolve and so on. But what you can see from this is, if I take the limit k to be small, then this term is not important. Which means at relatively larger scales, the pressure term can be ignored. Okay. What I will do is I will write again a few quantities which will be interesting. So let us define something called xj, which is Cs by h naught 2a by 3 omega. This is known as Jeans length or Jeans scale. This basically is a competition between pressure, which is encapsulated in the sound speed, and gravity, which is coming through this omega m term, which is basically the amount of matter you have. Okay. And if I put this back, what will happen is then, so basically you can write Cs in terms of xj. You can show that if xj does not evolve, which is not a good approximation at all, but suppose I assume this, you can show that delta B of Tk will be delta dark matter of Tk by 1 plus xj square k square. This will be the solution under the assumptions we have made. So again you see, so if kxj becomes very small, then delta B is equal to delta dark matter. So the effect of pressure can be ignored. So now you can ask, at what scales can I ignore the effect of pressure? At scales much larger than the Jeans scale. So Jeans scale defines that scale beyond which the pressure effects can be ignored. Okay. At smaller scales, there is a damping because of this quantity sitting. Okay, so the baryons cannot collapse very easily. The pressure starts resisting. A similar equation will hold for the velocity of baryons as well. So I will. So at this point, for the rest of the course, most of the time, we will be interested at scales which are much larger than Jeans scales. Jeans scales are typically of the order of 100 kpc to at max close to MPC. Okay, so they are not like really large. So at the cosmological scales we are interested in, you can safely assume that the baryons are following dark matter. So in those cases, as far as perturbations are concerned, so in those cases, we don't have to distinguish between them. So from here on, what I will do is I won't distinguish between baryons and dark matter, and I will just call them delta matter. Okay, and be done with it. Baryons will again play an important role when I talk about galaxy formation, because unless you form stars and things like that, there is no gravitational wave events. But that will come somewhat later in the course. So for some of the next few lectures, this is what we are going to assume. So this is delta m, and delta omega m is omega dm plus omega b, which is 0.3 something. Okay, so baryons and dark matter, the difference between them is now gone for most of these lectures now. Okay, it will come back later. Okay, maybe this is a good time to stop. Thanks.